High-performance computing has been enabled in version 3 through the Message Passing Interface, or MPI. In this video, I will show you how to access MPI parallel computing to speed up thermal analysis of a large FET. MPI is primarily a way of handling communication between parallel processes with distributed memory, such as the compute nodes in a cluster. The OpenMP interface, on the other hand, is used for programming parallel threads that access a shared memory, such as the threads running in the cores of a desktop computer. The SYMMIC desktop application has only shared memory parallel computing, but the command line utility xSYMMIC uses both OpenMP and MPI to speed up computation. If you run the xSYMMIC command at a command prompt, you'll see that it says it's starting xSYMMIC with 4 OpenMP threads, meaning that it's using only OpenMP parallel computing. This is the same as what the SYMMIC desktop application reports in the console when it starts. To take advantage of MPI parallel computing, you must use the MPI process launcher MPI exec. When you do this, you'll see that xSYMMIC switches from using OpenMP threads to using MPI processes. You'll also see that SYMMIC uses a different type of solver to solve when using MPI. SYMMIC uses the Intel libraries for MPI. So if you don't have MPI installed, you should follow the link in the user's manual. Under Getting Started, Windows installation. The Intel MPI library is available for Windows and Linux, and xSYMMIC runs on both operating systems. The big advantage of MPI over OpenMP is that the processes can be distributed to other computers to speed up computation. As a simplistic example, suppose I wanted to use my office mate's computer, Cape32, to solve my problem. I can use MPI exec to do this, provided I can log on to host Cape32 with my current credentials, and the working directory is a shared network folder, in this case, users public on Cape29. The more common scenario is to use MPI exec on a Linux cluster, which is explained further in the user's manual. Another advantage of the new iterative solvers written for MPI is that they use less memory than the direct solver because they do not require complete factorization of the system matrix. This may allow a big problem to be solved faster when memory resources are limited. Consider this example of a large FET device. This problem requires the solution of 5 million simultaneous equations. When I try to use the direct solver, I get an error message that there's not enough memory available to hold the factorization. Prior to version 3, the only alternative was to try to solve the problem out of core by storing the factorization on the hard drive rather than in memory. Unfortunately, the out-of-core direct solve took almost 8 hours on my desktop machine. In version 3, I have another option, an MPI iterative solver. I can access the MPI solver from the command line by using MPI exec without a host or host file so that the solver runs on my desktop. The default MPI solver computes the solution in less than 10 minutes, 48 times faster than the out-of-core direct solver on my machine. In conclusion, MPI parallel computing provides the scalability to solve big problems faster in version 3.